Ah, 1, 2, 1, 2. Very good. We're on. Sorry for the slight delay. We had some technical problems here with the projector. So, good afternoon. Thanks for coming. My name is Terence Barr. I work for Oracle. I'm a software engineer by trade. I've been doing Java development for many years. But lately, I've also taken on the role as product manager for Oracle's small embedded Java products, which I believe is actually the most exciting space coming up in the next few years for Java. And so I'd like to talk a little bit about where we see Java going, some industry trends, why we believe Java is, I think, the premier technology for embedded, and what we can do together to make this a really successful space. I also have a demo at the end. Hopefully the demo gods are with me and everything works. I've had some network problems, but let's see. All right. So here's what I want to talk about. So briefly, give you an introduction. Many of you might be new to embedded. Actually, I've noticed, the last couple of years at Devoxx was about, enterprise software, about middleware, about scalability, about programming methodologies. And this year, I'm seeing a lot of toys, a lot of embedded devices. I'm seeing robots. I've seen, NFC. I'm seeing lots of things that people play with. And this is part, I think, of a bigger industry trend that I would like to talk about. So, what I call the third IT revolution. Then I want to go into a brief overview of one of these products, actually the product I'm responsible for, Oracle Java Me Embedded 3.2. Then do a bit of a deep dive, some of the functionality in the APIs to help you understand, what you can do with this product. Try this demo if it works, and some closing notes. So I think one of the reasons we are seeing so much excitement in the embedded space today is basically three reasons, right? One is hardware is becoming cheaper and more powerful, have more memory, and devices are becoming more connected at the same time, right? The connectivity is not always, permanent. It might be intermittent, it might be wireless, but nevertheless, more and more embedded systems have connectivity out of the box. And then we're seeing a shift in the industry. It used to be that embedded was very hardware-centric, right? That was the value of an embedded solution, was the hardware that you're deploying. But as in the rest of the IT industry, more of that value is moving into the software stack and into the service area. And so if you take that all together, increased price pressure, pressure to create solutions, put solutions out into the market quicker, to make them more scalable, to make them live longer and be flexible and updatable in the field, right? All these things together is a clear shift away from traditional embedded solutions where you basically built the entire stack. You built everything from the ground up. You designed your own hardware, you implemented your own OS, you integrated all the hardware and the software together, you wrote your apps, you did some backend connectivity, you wrote some backend services to connect to that. Sort of point solutions for a single use case, but that's just not scalable anymore. It's too much effort, it's too expensive, it takes too long to migrate from one solution to another. So taking all these things together, this is just sort of a rough sketch of what I think we're seeing. The order of magnitude, we can argue, some people say, there will be 10 billion smart connected devices over the next few years. Other people say 50 billion. But in any case, it's very likely going to be a very large number. But if you look at sort of the history of IT, of computing, we start in the 60s and the 50s with the mainframes. Very few devices in the world. Many people, the people to device ratio was n to 1. You had many people using one device. It was not personal at all. Very little traffic, very small unit volume, obviously, of mainframes. But then sort of in the 80s, 90s, 2000s, we got into the age of the internet, right? Of desktops, PCs, mobile phones, where you had a one-to-one relationship of people to devices, more or less. But what we're seeing now is having many connected devices out there, many more devices than there are people. to make the environment smarter, to drive better business decisions, to sense what's happening in the real world, and connect that data back into the enterprise. And so the red curve is sort of this explosion that people are expecting, but more interestingly, because these devices are all connected, we're going to see an even greater explosion in the traffic that these devices are capable of creating. Because they can talk between each other, they can talk to the back end, and this is actually one of the critical aspects of the Internet of Things, is to be able to manage that explosion of data. The carriers, the wireless carriers, are actually scared because they can already not deal with the traffic that smartphones generate. How bad is it going to get if you have a 10-fold or 100-fold increase of devices out there on the network creating data? So there's lots of opportunity in the space, obviously, but there are a couple of headaches, right? If you think about billions of devices out there, how are you going to manage those? How are you going to make sure they're secure, the data is secure? How do you develop software and services for them? How do you update them while they're in the field, right? How do you create applications in a scalable, cost-effective manner? I mean, you can't afford to custom build applications for hundreds of different device types, right? Not everything's going to be a Raspberry Pi, not everything's going to be a BeagleBoard. There's going to be a wide range of devices and platforms that you need to support. So, actually, I'd like to skip straight to here. Oops, is that broken? No, looks broken on my screen. All right. So, we believe this market can only really take off if there is a common set of standards, a common platform, and a common way to develop software and services for these devices. We need a horizontal platform that people can build upon to then really add value on top. If everybody keeps building, reinventing the wheel, we're never going to get to really harness that opportunity. And so if you look at some of the things, some of the key challenges that you have in this space, right? Things like robustness, like the ability to have a device out in the field for 10 or 20 years and operate in a reliable manner, to be able to update it while it's out in the field and add value or add fixes or change the way your algorithms work. One of the things that's really important is turning data that these devices generate or sense into information. That's really important because sensors can generate a lot of data, but a lot of it is meaningless or only useful if it's analyzed in a context. So what you need to do is actually filter the information at its source and make sense of it and distill it down to the actual things that matter to you. For example, if you're monitoring temperature in an environment, right? You don't want to have a temperature value sent up to a server every second. That makes no sense. It doesn't tell you anything. What you want to be able is to have the device be intelligent enough, run a local algorithms to filter out and only tell you when the temperature exceeds a certain value, for example, and it senses an alarm, and that alarm is sent back to the server, right? Not every little bit of data. You want to be able to separate the hardware from the software. I think that's another very important point in traditional embedded programming. Because your native code is so tied to the platform specifics, it's tied to the hardware, to the OS, to the libraries, to the tools. Typically, software and hardware development are sequential, right? So you start your hardware development, and only when the actual target hardware is available, you can start doing software development, right? So that increases your time to market. What you want to be able to do is start developing your software before the deployment hardware is even ready, right? Of course, Java with the virtual machine environment allows you to do that, right? So many good reasons to choose Java. I think I'll skip over this slide. I think there are a lot of obvious advantages of choosing a virtual machine, platform and Java over native. Many good reasons. So I think to the Java folks here in the audience, that should be sort of self-evident. But what's more important is it's not just about the device. and the software and services that run on the device. Once you have these devices out in the field, you really need to capture the data, right? That's where the value is, the data that these devices generate. So that goes into some sort of cloud, gets transmitted to a back end, and that's where the value really lies. When you start analyzing the data, you're doing analytics, you're doing post-processing, you're meshing it up with other data to create more valuable information to be able to make business decisions. For example, if you're on a factory floor, right, and you have all sorts of sensors that monitor the production process, and you're able to, in real time, distill that data and find out that some part of the production process is not optimal, right? And then turn around and feed changes back into the device so the devices actually can affect the way the production process is happening, right, in real time. And Oracle as a company, you know, not only does Oracle have all the Java IP, of course, but Oracle as a company is uniquely positioned to be in the space because Oracle also has, of course, a lot of back-end infrastructure, back-end services, back-end products that already play in many of these verticals, you know, like logistics or healthcare or energy. So that's, you know, that's really the motivation. Of course, the more data and the more intelligence is on the edge of the network, the more valuable your back-end services become and vice versa, right? Okay, so before I go into the details of the actual product, I'd like to talk about these two releases that we did at Java 1. So Java 1 was really all about defining Oracle's embedded Java vision and strategy. Oracle has realized that this is a huge space. Java is a really good technology for this. And in fact, I don't know how many people were at Java 1. There was actually a dedicated sub-conference at Java 1. It was called Java Embedded at Java 1. And that was a 2-day conference dedicated to embedded Java and M2M, the M2M ecosystem. So 2 new products were released a couple weeks ago at Java 1. One was the product I'm responsible for, Java Me Embedded 3.2. So that is a Java runtime specifically optimized for resource-constrained devices, very small devices that sit on the edge and add intelligence to the edge of the network. And then there is this other product called Java Embedded Suite 7.0, which is basically a slimmed-down middleware stack. So it's Glassfish, it's JavaDB, and it's Java SE embedded. So it runs really well on sort of mid-range embedded platforms, you know, maybe like a Pi, for example, on Linux ARM, and it's more geared toward that middle tier where you're doing some concentration of the data, where you're managing devices, where you're doing adding intelligence around the data and integrating that with the backend. So those are the 2 new products. So we'll spend the rest of the talk on Java Me Embedded 3.2. So to give you an overview where things sit here, so some of you might have played with Java SE Embedded or OpenJDK on the Pi, for example, on other Linux systems, right? So that's more on the right side, sort of the medium and high end, right? If you have a decent amount of horsepower, you have a decent amount of memory, anywhere from 16 megabytes upwards, or for Java SE you need even 32 or 48 megabytes. You have a fairly powerful processor, and you can afford the BOM cost of all that hardware, then Java SE Embedded is a good solution. If you want to go lower, and that's where we think the volume is, right? The really small devices where you're talking a couple of euros per unit. Interestingly, and that's something I learned from a discussion with Intel the other day, the major cost in hardware today is not the processor, it's not the I/O, it's memory. It's dynamic memory. RAM is the cost that determines the BOM. And so if you want to go after devices that are a few euros, you need to go into the low end and really conserve memory space. So on the small side, so we're talking about general purpose CPUs like ARM Cortex-M, ARM Cortex-A CPUs, but where you have memory constraints, you have a couple of megabytes of memory at best, right? But you still want to run a full Java environment. You typically have a bunch of connectivity, either wireless or wired. You have connectivity for I/O, right? So that's the space we're talking about, the right side of the small. The far left is Java card, which is really a specialized environment for secure applications. So we released this product. Give you a general overview. So Oracle Java Me Embedded 3.2 is a general purpose Java runtime, which is optimized for resource constrained ARM systems at this point. It's very flexible. We can port it to other architectures. It is based on the existing technologies that we've been shipping into the mobile space for many years, into feature phones. So it's a very robust platform. And we've enhanced it with a couple of features that are specifically relevant for the embedded space. So if you look, for example, at Java SE Embedded, it's lacking a few key features that you really need in the embedded space. We're adding those over time. But one of the things that is difficult in Java SE Embedded is accessing devices. Right? You often have to install native drivers. You have workarounds like mapping GPIO memory via memory map operations, installing drivers, and there's no standard way of doing it. So we've added a bunch of features into this product that give you a horizontal platform to develop embedded applications in a standardized way. You don't have to mess with the system anymore. You don't have to install drivers. One of the other really important things, and I've talked about this before, is the ability to update devices in the field. Right? So if you have an embedded device in the field and it sits there for 10 years, for 15 years, you need to be able to push new software into that device. Let's say, for example, you have a smart meter device and the regulatory guidelines change. The law gets changed, and there are things in the way that you treat the electricity consumption and the data that you're handling. You have to change your algorithm, right? So it's just not practical to go, and send people out to millions of homes and manually update the software in those devices or replace the devices. Just not feasible. So you have to be able to push devices out into, push software out into the field and update the software on the devices seamlessly without affecting the integrity of the device, right? You can't have a software problem while you're updating and then millions of devices stop working, right? So it has to be very robust, has to be very secure. And you might have different types of hardware out there in the field, right? You might, over time, have deployed different types of smart meters into the houses, so you have different platforms. You don't want to be in the business of having to recreate that application for 20 different hardware platforms just because you have to do that update, right? You really want the software to run in Java, and so you don't care about the underlying hardware. In fact, that was one of the reasons Électricité de France chose Java for their smart metering system, because they had to multi-source the hardware. That was a requirement by the government, and they only wanted to develop their applications once. We'll talk about some more about the VM itself. There's a tool chain that comes with it, and I'll show you a demo. So the VM is, again, for purposes of robustness, for purposes of resource, optimizing the use on resource-constrained devices, we've tuned the VM in multiple ways. So it can run very reliably over long periods of time. It's fully multitasking, so you can run multiple applications in parallel in isolation, even though you don't have to have an MMU underneath and you don't need many megabytes of memory. You still have a very robust multi-application system. The devices that we're targeting are typically headless, sort of deeply embedded. So everything you can do on this system, on this product, works headlessly, including configuration of the device, remote debugging. Everything's headless. We support a variety of network connectivity, both wireless and wired. And the system is remotely configurable and remotely, you can remotely operate it. So You can connect to it remotely. You can start and stop applications. You can install applications remotely over the air. You can reboot the system. It can automatically start up applications after hardware or software failure. It'll just restart and restart all the applications that you've configured. And then finally, as I said before, this product is targeted for the really low-end device space. So we can operate on microcontroller class devices with as little as 130 kilobytes of RAM. And that's not some chopped down, dumbed down version of Java, but it's actually a pretty decent CLDC virtual machine. So I'll talk about that later as well. So here are some of the specs of the hardware that we're targeting, just to give you an idea. So currently, we're looking at basically the current range of ARM architectures. So we're targeting a wide, range of platforms in, ARM together. The different ARM platforms together and ARM architectures together cover about 70% of the embedded market today. So we can cover a wide range. The operating system, people ask, well, do I need Linux or does this run on Linux? Well, you don't really want Linux on these systems. You can't run it anyway. There's not enough memory. But if you think about it, Linux, what does Linux offer you? If you write your applications in Java and you have access to all the hardware that you need and everything else that you need, you don't really need an operating system like Linux. It's overkill for these types of situations. So all we need is a very simple real-time OS, and there are many of them out there. And the porting is actually pretty straightforward. If you need to go to some obscure real-time OS that we don't happen to support. I'll talk about the peripheral I/O. I mentioned the footprint, so we can very comfortably run in about 1 megabyte of RAM. You can write some decent application code, fairly sophisticated code in 1 megabyte of RAM. The typical use cases that we're targeting is really our first customers are in the area of wireless modules. So these are small, smart devices. Think of them like a cell phone without a screen and a keyboard. So they have wireless connectivity, they have processing power, memory, they run a Java runtime. They're very versatile, and I'll actually talk about a use case. But more general, we see industrial control is a big sector that we're looking at, smart metering, e-health or telehealth, and then just generally the machine-to-machine space, so where you have smart devices on the edge of the network talking to each other or talking to a backend. Whenever you want intelligence locally in your embedded solution. So let's go into a little bit of more detail. This is a slide we'll spend more time on. So this is the sort of the modular stack of this platform. If we start at the bottom, it's a bunch of I/O. So we support all the things you can see here: networking, file I/O, GPS or location services, various industrial buses, I2C, SPI. So it's very, very easy to talk to devices and sensors that are connected to the system. As I said, device operating system, we don't actually need very much. A small real-time kernel is enough. It doesn't even have to be real-time. Small kernel is enough. It's very portable, so if you need to port to some specialized deployment platform that, for example, your customers are requiring, the porting is actually quite simple. We've optimized this porting layer over the years. We have a CLDC virtual machine, so if you're not familiar with CLDC, it's what's used in feature phones. It's been around for a number of years. It's basically a cut-down version of the Java language spec and APIs. So it's not quite up to current standards like Java 7, for example, but I'll actually talk about that more, how we're developing that or evolving that. But you still have a pretty rich Java runtime. You have multitasking, as I said. You have full on-device debugging, so remotely onto the board. Then we have the profile called IMPNG. People might not be familiar with it. It's basically mid-P without any of the graphics. So it has an application model, it has a bunch of libraries and APIs that you can use. And then on top of that, we have a number of APIs that are optional depending on your specific use case. So on the right, the blue boxes are standard JSRs that are just defined through JCP that have been around for a number of years. Like you can do XML processing on the device, you can do you can consume web services, you have file I/O, location-based services. So it's a pretty rich platform, right? If you look at traditional embedded Java, or sorry, traditional embedded development, native development, you have to build that stack yourself, right? And you have to take all the different components and integrate things, and then you have to cross-compile them down to your platform, and nothing's really standard. Everything's customized, and it's really difficult as a developer to deal with that. It's a very specialized set of knowledge and experience that you need. Whereas here, you just take your standard Java programming experience, you look at the APIs on the web, and you use NetBeans or IDE, NetBeans or Eclipse, and off you go, right? You're an embedded Java developer. It's really important to us that this is a horizontal, standardized platform and not something that's specialized, where you spend weeks and weeks understanding what you need to do. The only limitation, of course, is that you have a limited amount of horsepower and memory, so you have to make sure that you don't allocate large arrays or do really heavyweight processing, because the CPU just won't deal with that. On the far left, the green boxes are additional APIs that we added to target these embedded use cases. So I'll talk about these in a little bit more. So there's the device access API. That's the one I mentioned before. That's an API that allows you to access all the I/O at the bottom in a Java, platform-independent, hardware-independent manner. And you can essentially write Java device drivers that use that API to fiddle the bits on the buses and wrap the data that you're getting into some nice class, some nice data model like a temperature sensor or something, so that the application on top just does, get temperature or something, and all the complexity is abstracted away from the application. And then, of course, you could take that application and migrate it to a different platform where the I/O is completely different, but it still works the same from an application developer perspective. We actually plan to standardize this JSR, standardize the device access API as a JSR, and also make it available on Java SE, right? So today, if you build an application with Java SE, you have exactly that problem. There's no good standardized way of talking to this I/O. So we plan to make that available as a standard. And again, you'll be able to create an application talking to I/O on a very small platform, and you can take that very same application and put it on a big honking Java SE system with many megabytes of memory and a gigahertz CPU, and it'll run the same way, just much faster, right? We have the access point API. That's actually an interesting one. If you're out in the field and you have wireless connectivity, like GSM connectivity, for example, that connectivity can actually be very poor, right? You're in the middle of nowhere, you have a very poor connection, it might be expensive. So what's state of the art in this field is actually to have multiple connection options. So like, for example, 2 SIM cards on the device. And so if for some reason your connectivity goes down on one carrier, you can actually switch over, the application gets notified, there's an API, you can listen to events, the application gets notified and can then switch over based on your policy, on your application policy, your business logic, switch over to another carrier. Maybe that carrier is more expensive, but more reliable, and so you can use that, you can reduce your data rate, back up data somewhere, just do the absolutely necessary communication, and at some point when the original connection, the cheaper connection comes back, you fail back over, and then you start pushing all the data that's been backed up, right? So you really want to be able to allow the application to make intelligent decisions, because that gives you, better service, better value of the data that's being created or being sensed. We have a logging API, so you can log all the, you can remotely monitor what your application is doing. You You can log that and then create connectivity to the back end where some remote management server gets all the logging information. We have this AMS API, so you can actually create an application that completely controls what happens on the device. So the AMS API is application management system. So we have a complete API that allows you to install, start, stop, pause, remove applications under application control. So you could create a system controller application, for example, that interfaces with your backend remote management server and receives, if you want to provision a new application, it receives that application, stops the old version, installs the new version, restarts it, right? So you really want to make sure that everything happens under your control and is remotely manageable, because these things sit out in the field. They might not be even accessible once they're deployed, right? So it has to be remotely managed. On the far right, we have tools integration. I'll talk about that a little more. So we have plugins for NetBeans, plugins for Eclipse. So you can write your applications just like you are used to on other Java runtimes. They deploy down to the device. You can do real-time source level debugging directly on the device. So this is nothing special for Java developers, but for native embedded developers, this is heaven. For them, this is typically much more difficult. So I actually think I spoke about most of this here. Yes, maybe the last point, OEM extensibility. So one of the tricky bits in the embedded space is there is no generally accepted solution, right? There's every embedded use case has its own challenges, its own requirements, and you can't just say there's one platform that covers it all. You need to be flexible, right? So we have to be able to easily extend this product with additional functionality. So let's say, we are not in the business of building intelligent vending machines. We'll have a partner to do that. We give the partner this product. They can add extensions that target the vending machine space, specific functionality. They'll repackage the product and use a system integrator to integrate it with the vending machine solution, right? So that can easily be done. Let's talk a little bit more about the JSRs. I mentioned them before. These are the standard JSRs that you can use. File I/O is pretty obvious, so you can store data in files. JSR 120 is the wireless messaging API, so that essentially allows you to send and receive text messages, SMS messages. That is kind of old-fashioned, but it works really well actually for remote management. So text messages are asynchronous and pretty much always work. At some point the system will be able to deliver that message. It's more reliable in that sense than a data connection. So what our customers typically do is they use SMS messages to trigger functionality, remote management functionality, right? So for example, stop an application or reset the device, or any type of application functionality you can trigger through SMS messages, if that's what you want to do. We support 172 for web services, so you can easily talk to web services that are sitting, in your backend, for example. I mean, that's one of the strengths of Java, right? Because you have Java, you can support all the standard protocols that people are doing on the enterprise backend. JSR 177 allows you to actually integrate with a SIM card. If you had a SIM card on your device, for example, to store data securely, right? A SIM card has an encrypted, secure location to store data as a secure element. So if you wanted to store, for example, secrets, keys, other important data that you do not want anybody to ever see, even if they get hold of the device, you can't actually, nobody's ever managed to reverse engineer data out of a SIM card, out of a Java card. So you're able to talk to that and basically interact with that SIM card and store data if you need to. JSR 179 is location-based services. That should be pretty obvious, and then XML processing. So if your backend if you interact with your backend in XML, then you can do that as well. It's all there. So none of this matters if you don't have a platform to run this on. That's the challenge in the embedded space. As I said, there are so many different platforms. You have to start somewhere. So what we did, this is the first release. So what we did is we have an emulation runtime for the Windows desktop. And I'll show you in the demo. It's integrated with NetBeans and Eclipse. So you just basically hit the run button and it just runs your application in the emulator. So it's very easy. That's available today. We have a binary that we're making available for these ARM Cortex-M devices. This is one of these boards. I'll show a picture in a second. So that's an evaluation or development board from ARM, and it's a complete runtime with 2 megabytes of memory. And you can develop your applications. You have access to all the I/O. That's coming soon. We ran into some last-minute red tape, so we're getting through that, and we'll post it on OTN soon, and it'll be free for download. Basically, what you do is you download the binary. We have a getting started guide. You flash it onto the board. You hit the reset button, and off you go. You have a Java runtime on your embedded system. We're working with a number of other vendors to create platforms for various target verticals and use cases. So we have a company called Centurion, and I'll talk about that on the next slide. We're working with Qualcomm. They made an announcement. They want to use Java as their standard software runtime for their M2M device line. So they have a dedicated M2M business unit that's attacking this space. And if you need, we're working on other platforms. I can't talk about them, but stay tuned. We have some interesting things coming in terms of platform support. If you have a specific solution that you have in mind, and you think, oh, this product would be perfect for my particular deployment scenario, but you have a very specialized piece of hardware that you need to support, then come talk to us or one of the Oracle partners, and we can build you a solution, or we can enable you to build a solution, depending on your needs. So this is one use case. Centurion is a company in Germany. They're actually a spin-off of Siemens. They've been around for a number of years. They're actually the leader in the wireless module space. So these are devices that have a wireless radio on them, 2G, 3G stacks, and they're full-blown little computers. So they have an ARM CPU, they have RAM, ROM, I/O. You can plug in a SIM card. And as I said before, they're like phones without a keyboard and a screen. And they're really ideal if you want to make a solution that you already have, or you want to build something new, and you want to add intelligence and connectivity to your product, right? That's ideal. So, for example, vending machines. There are vending machines companies are now starting to make their vending machines smart. So they're putting these modules as retrofits into the vending machines, hooking them up to the hardware. And so now they can remotely monitor the supply levels in the machine, the temperature. They can automatically trigger messages to the company that supplies and restocks the machines. They get fault notifications and all that. You can use it for container tracking, for example. Huge problem in the logistics space is containers actually get lost. Some amazing thousands of containers every year get lost. They just don't know where they are. They're parked somewhere, maybe in a big pile of other containers. You can't get at them, and they're just lost, right? So they use these modules to track containers to make sure they're not broken into. You can actually do mesh networking, right? So the containers are shielded metal. You can't, if there's a container in the middle, it doesn't have, there's too much metal to connect directly to an outside wireless tower. So what you do is you enable mesh networking. So the containers around it relay the information, relay the signal out. So you can actually you can find a container even if it's in a mountain of other containers. So lots of interesting use cases.
Temperature, by the way.
Sorry?
Also temperature, by the way, yeah.
And
Incredible source of information that they're also monitoring the temperature for certain containers.
Oh yeah, temperature. You want to make sure, for example, that if it's expedited freight, right, that you can actually real-time monitor the progress, the transition of the container, and if it gets stuck somewhere, you can immediately take action, right? Why has this been sitting here for 4 hours, right? It needs to keep moving. So there's just, the possibilities are almost endless. And so Centurion has chosen Java as their core runtime for all of these new devices. And so first of all, they understand that Java is just a really good solution from a developer perspective. But more interestingly, one of their problems is because these guys have a radio stack in them, they have to be qualified and certified in each country, right, to make sure that the radio stack is, abides by all the laws and regulations. The radio stack is written in native. And what you don't want to do is add native software to this module, because every time you add native software, your application, for example, native code, every time you add native software, you have to re-qualify the device. You could have broken the radio stack, right? It's a requirement. And just re-qualifying a device takes 6 months. So what they actually are doing now is they're making their native layer as small as possible, and they're implementing all the application logic, all the intelligence, everything else in Java, because you can update the Java logic without affecting the functionality of the runtime. Same thing for, or the functionality of the device. Same thing for the automotive industry. Every device in automotive has to be qualified. Once you fiddle with the native stack, you have to requalify. Same thing. You need to implement everything on Java, run it in a sandboxed virtual environment, right? It just makes business sense. So here's the platform I was talking about. So this is kind of a high-end developer platform. It's around 350 euros. So it's not something that you would buy thousands of. But that's not the point. It really just breaks out. The reason it's so expensive is because it breaks out all the I/O on the SoC, on the chip. The ARM Cortex SoC is actually one of those smaller rectangle chips on there. Everything else is just I/O. You can buy this online at distributors, and we're supporting a bunch of the I/O on it. And as I said, very soon we'll be making available that binary that you can download from OTN and just flash it on the device, and you have the Java runtime going. Here's one example that we've been demoing that we put together actually fairly quickly. It's a solar tracking type industrial application. So we have, unfortunately I don't have a demo video with me, but we have a pan tilt unit on the left. The solar panel is actually missing. That would be on top, of course. And we have a light sensor. And the idea is that you can position the solar panel depending on your needs, right? Either to maximize power production of the solar panel, perpendicular to the light source, or you can track other things. You can implement different tracking mechanisms, like you position once, you need to let it sit there, or you position continuously, or you do testing, right? So there are a number of different algorithms that you can implement in Java. We control the servos through a servo controller that's hooked up via serial. We have a light sensor hooked up via I2C, so that's an industrial serial bus. The applications, there are a number of applications running on the runtime, and you can actually, as I said, start and stop the applications. You can add additional applications. They run in parallel. You can have one application, for example, that monitors the sensor, one application that drives the servos, one application that talks to the back end. So we have an integration with a Glassfish server sitting on the back end to push statistical data up. We actually have a Java FX client running on a PC that monitors the state of the system on a continuous basis. So I'm actually planning to put up a video on YouTube one of these days with the demo so they can find out more. But the idea here is just to give you a sort of a sense what you can do with the system. You can do pretty interesting things. You can run fairly sophisticated Java applications on these and really control and sense the environment. Okay, so let's have a little demo. We have 12 minutes left. So this is really simple and just scratches the surface. But I wanted to show you one example. I spoke about this device access API, so the ability to talk to devices that are connected to your system in a platform and hardware independent manner. So this is the GPIO manager class here is part of the device access API. So you just basically say, okay, GPIO manager, give me an object that represents one of my LEDs, for example, right? So the LEDs are on the GPIO bus, so you get this LED, LED1 object. You then get a button object, which is also hooked up to the GPIO. So if you look at this device, there are a number of LEDs and buttons here. And then for the button, of course, you want to listen to when it's being pressed. You can listen to any change in value on an I/O pin, obviously. So we create a new button listener or a new pin listener, sorry, and when that value changed method gets called, we basically get the state of the pin printed out and then set the LED value accordingly, right? So whenever you push the button, the LED goes on. When you let go, it goes off, right? So very simple, but this is the kind of stuff in Java SE, and we had a talk yesterday here, the JavaFX bootcamp, I think it was called, where Angela showed this robot arm and a couple of other things, and they had to do pretty clumsy, mapping memory via the mmap Linux device and have a specialized device driver to do that. And of course, that's not portable. So this is what we want to do as a standard going forward. But it's already implemented in this product. So let me just quickly show you how that actually works. So quick demo with NetBeans. And I'll switch to okay. So what I have here is I have NetBeans. You can just use the latest version of NetBeans, and you download the Java Me SDK 3.2 from OTN. That comes with the support for this new platform. So there's a new platform in there, Oracle Java Me Embedded. And NetBeans detects that Java platform, and then it's just another Java platform, right? If you go into NetBeans and you look at Java platforms, oops, you'll see there's a new platform there, right? So it's just like any other Java platform in NetBeans. So I can create my demo. Important is that in the properties, I set my platform. So CLDC, micro, Java Me. What's the full name here that we have? Oh, okay, just the Java Me SDK 3.2. It gives me the various APIs that are available. Those are the ones I spoke about. So you can compile against these APIs. And here is the GPIO demo. So it's really just a single file, very simple. So everything extends midlet. So that's the heritage IMPNG has from MIDP. So that's your application model. The system starts and stops application for you. So there's a start app that gets called when the system wants to run the application. There's a destroy app. There's a pause app. So that's just the application model, just a few methods that you need to implement. The real code happens down here. Right, so this is the code example I showed you. The button listener, so we create this listener and it just prints out a message when we push the button and it lights up the LED. So to run this, where am I? Right, so we choose a device here, which is the emulator. So we just run the app. This Windows 7 virtual installation is a bit slow. Let's see how long it takes. It should pop up. Okay. So it pops up this is the emulator now. So you can see it already started the application. And it says, so here's the AMS tab, so that's the application management system. You can see the commands that you can actually operate on the AMS. So you can start and stop and install. You can look at what is this application that's running. So you really have a full-blown application, multi-application management system on here. And then you can look at the state of the device. So the application is started up, and we're emulating these 2 LEDs and these 3 buttons here, and all of them are off. And then we have this events generator. So now we can basically inject events into the system, and we can say, all right, we'll pretend to be pushing this button. Okay? So the GPIO pin listener, you can actually see it down there. You can see the listener method being printed out. And the emulation now actually says, okay, LED 1 is on and button 1 has been pushed, and vice versa. I push it again and they go off, right? So very simple. And you can actually emulate a bunch of stuff here. So you have all the GPIO pins. You actually have emulation of the I2C bus, of the SPI bus, and memory mapped I/O. If you have some odd device that doesn't fit into any other category, you can use that. You can also emulate GPS events. So you can write location-aware applications. You can switch between multiple SIMs. So there's a channel, communication channel emulation, and so on. Because we're short on time, I'll forego the demo here on the hardware. It actually works exactly the same. You just hit the run button and the application runs on the hardware. You push the buttons and the LEDs light up. And that's the whole point, right? It's seamless, integrated application development like you would expect it in Java. Only it's running on a tiny microcontroller type system. So I have 2 or 3 more slides. Okay, so here's the roadmap that we presented at Java 1. So the upper part is tools and Java SE and Java Embedded Suite. So those are the larger embedded products. You can find this online. I don't want to spend any time on it, but we'll look at the lower part, which is small embedded, so Java ME embedded. So we're obviously, 2012 in the middle. That's the release that we're talking about, including the tools, ME SDK. We plan the next release, 3.3. We have a pretty aggressive timeline for beginning of next year. We'll enhance the device access mechanisms to support more types of hardware. We'll support more platforms. We'll do more optimizations and configuration options, so it's even more portable, and you can make the memory consumption even smaller. And we'll improve the developer experience and tooling as well. And then for next year, mid-next year, around Java 1 timeframe, that's going to be a big bump in terms of functionality. We plan to introduce Java ME 8. So if you have been following Java 1 and the announcements, the plan is to align the Java SE platform and the Java ME platform in terms of features, in terms of APIs, libraries. So the idea is that from a developer perspective, you have a similar set of libraries, tools, and APIs. You can actually use generics and annotations and all the nice things that you have in Java SE today. You will be able to use this on the small platform, so that's more code portability for you. You can reuse old libraries, for example, while maintaining the footprint, right? So we're implementing all this, and we still plan to run in 1 megabyte of RAM. NetBeans will be updated accordingly to support all the new language features and API features that come with ME 8. And then we actually have a bunch more in store that hasn't been officially announced, but I'm personally very excited about this space. I really think that this is sort of Java's next big wave onto billions of devices where Java will be very, very prevalent. And it's a great opportunity for developers because I believe there's a lot of software, and a lot of services, and a lot of solutions that need to be developed for this space. So it's a big opportunity for, for developers. That's pretty much it. Here are some links, and if you want to get hold of me, just use my Twitter handle, @TerrenceBarr, or check out my blog. I'm not blogging as much as I would like to, but I try to at least cover the major sort of things that are happening in the embedded Java space. With that, we might have time for one or two more questions. Anyone? No? Okay. Thank you. Enjoy the rest of DevOps.